Greetings, my name is Professor Duke Orata. We are continuing with our lectures. So when we look at ducts, we remember, for example, in talking about flowing ducts, that we have that graphical expression where we had the ratio, final and initial pressure, and of course we have the expression for velocity, specific volume, and therefore area. Let's call that for area A1, and that one for velocity, specific volume V1, and for velocity, initial velocity C1. This, of course, will be C2. That will be V1. That will be A. That will be V2. That will be A2. And remember, we said that this minima here represents the critical pressure ratio. CPR is the critical pressure ratio. And it's important to remember or to note that at the critical pressure ratio, the flow in the duct is accelerated to the sound velocity. Flow of fluid in the duct accelerated to the sound velocity at the CPR. That's the critical pressure ratio. And it's very important to note that at the critical pressure ratio, the area is a minimum. Area is minimum. But the mass flow per unit area is maximum. Per unit area is maximum. Now, if you remember, if you go back to our lectures, which you have already covered, and I keep encouraging you to go through our lectures, with our lectures systematically, so that we don't lose anybody along the way. We saw that under isentropic conditions, we saw that dH was equals to V dP. And therefore, if we go to the steady flow equation, which we had derived earlier on, we have dH plus dC squared over 2 plus dDz, dQ plus dW. And we say that if the elevation from the datum level is not significant, then this potential energy expression is 0. And this is the kinetic energy expression. And you can substitute in place of dH, you can put VdP, so that dC squared over 2 now, dC squared over 2 will be VdP. Remember that kind of expression. And we mentioned that in most of the fluids, especially when we are dealing with perfect gases, for example, where the term fluid here we are referring to both liquids and gases, we can have an equation of state which relates pressure and volume. State relating pressure and volume. Very important for us to note that. And so, on the same premise, when we have from the steady flow expression, dC squared over 2 is dW, and that is P dV. There's something now we are used to in thermodynamics. P dV, if you assume, is P dV. Remember, we are assuming pressure, volume work, and that is P dV. If we are dealing with an ideal system, that is like a perfect gas, then we will have the polytropic equation for ideal gases. We'll have the polytropic equation for isentropic process, PV gamma will be a constant. And remember, gamma was the ratio of the two heat capacities, that's the isobaric and the isochoric heat capacities. These are under isentropic conditions. But when you are dealing with vapors, for example, in the case of vapor or steam, this gamma in the case of steam, where we are in the wet region, where there's still some liquid and of course vapor, gamma will be about 1.135. That's in the wet region. While if we are in the superheat region, we are not gamma, that's N. If we are in the superheat region, we will have the N have a value of 1.3, that is in the superheat region. So that the polytropic equation, in this particular case, is PV N is equals to K. And N, remember, is the isentropic. Expansion index. N is the isentropic expansion index. So once we know that, we can use the polytropic equation. We call that this, when you remember, we refer to it as a polytropic equation. And if you look at some of our lectures, earlier lectures, we have discussed polytropic equations. We can quickly move on to derive this form, whereby we have that is dc squared over 2 will be given by P dV. So if you use the polytropic equation, P1 V1 N is equals to P V N. If we make N our subject here, what do we have? If we have for P, we'll have P now will be equals to P1 V1 over Vn. So if you substitute that quantity there, of course integrating from some plane 1 to 2, we will have P1 V1 N over Vn. This is Vn, exponent, Vn dV from plane 1 to 2. So if you assume that the initial velocity is negligible, if you assume C1 is negligible, then our lives become a little bit easier. So that, what do we have now? We have C2 squared over 2 will be given by that expression 1 to 2 of P1 V1 N into V minus N dV. And of course, as usual, if we use the integral calculus identity, that is xn plus 1 over n plus 1 plus c, then we can take that expression there. So we'll have C2 squared over 2 is equals to P1 V1 N into V minus N plus 1 over minus N plus 1 from plane 1 to 2. So we can open up this expression there as we have done in the past. If you open up that expression there, then you have V2 minus N plus 1 minus V1 minus N plus 1 over 1 minus N. So let's simplify that expression further. So we have here, we have C2 squared is equals to 2 over 1 minus N. We've just removed that denominator there, wrote it out. Then we have P1 V1 N times V2 1 minus N minus P1 V1 N into V minus N plus 1. So once again, we can simplify this. Remember, we know that P1, recall, that P1 V1 N is equals to P2 V2 N. For harmony in terms of the functions, we can replace P1 V1 N with P2 V2 N, so that we have C2 squared as equal to 2 over 1 minus N into P2 V2 N into V2 1 minus N minus P1 V1 N into V to 1 minus N. And of course, using the simple arithmetic of indices, we have m to the x times m by y, that will be mx plus y. So we can apply those quantities there. So what we have, we'll have C2 squared will be 2 to 1 minus N into P2. Of course, that will be N plus 1 minus N, which will be V2, minus that will be P into V1 N plus 1 minus N, using that of indices, that will again be P1 V1. That expression is important for us, so in terms of velocity. Now, let us continue working on this so that we get the maximum velocity, expression for the maximum velocity for the flow in the duct. Once again, now, we still have C2, 2 and 1 minus N into P2 V2 minus P1 V1. But using the polytropic equation, use the polytropic equation, now that P2 V2N is equals to P1 V1N, and of course that is P Vn, which is a constant. Don't forget that. Very important for us. Always remember the polytropic equation. And now remember that for the ideal fluids or ideal gases, that asymptotic expansion index is gamma, which is the ratio of the heat capacities. Now, if we get the expression here where we have for P2, where we have P2, where we have for V2, so we have P2 V2N equals to P1 V1N. So P2 over P1 will be V1N over V2N, which we can factor out. So we have V1, V2N, and have V1, V2N. And so in this particular case, or we want to make our life easy, we want to have V2 the subject, so let's make our lives a bit easy, or we can have it as V2 over V1N is equals to P1 over P2. So V2 over V1 will be equal to P1, P2, 1 to the n. Remember, we just use the simple identity, don't get confused. M to the n is equals to k. This is the same as m is equals to k 1 over n. You just divide the exponent by that, simplify. So we just done that exactly there. So that what do we have? So we have V2 therefore is equals to P1 over P2 1 over n V1. So we can use this expression, we can substitute this expression into this equation. Let's call this equation 1, let's call this 2. So substituting 2 into 1, so substituting 2 into 1, we will have the expression now. Let's not erase it. The analysis we'll have C2 squared is equals to 2 over 1 minus n into P2, V2. So we have P2 and V2 is P1 over P2, 1 over n, V1 minus P1, V1 minus P1, V1. So let's call that expression number 3. And so if we further simplify, further this particular expression here, we can divide the quantities in the bracket by P1, V1, so that we make our lives easy. That will be 2 into 1 minus n into P2, V1, P1 over P2, 1 over n divided by P1, V1 minus 1. So we have just divided the quantity in the bracket here by P1, V1, and so simply divided by P1, V1, as P1, V1 is 1. And so if we expand this further, of course you'll see that V1s will cancel. V1s cancel, so we have C2 squared will be 2 to 1 minus n, 1 minus n into P2 times P2 minus 1 over n, P1 times P1 minus 1 over n minus 1. Remember, we just use again a small identity which we are used to. That is, if we have m to the n, that can be written as 1 m to the minus n. Very, very simple. Those are very simple laws of indices in arithmetic. So let us simplify this further. So C2 squared will therefore, C2 squared will be 2 into 1 minus n. And of course, this will be P2 into 1 minus 1 over n, P1 into 1 minus 1 over n minus 1. And what is that? If you open up that, if we simplify those fractions there, the index, we have 2 into 1 minus n, and that will be into P2, that will be n minus 1 over n, P1, n minus 1 over n minus 1. It simplifies further to P2 over P1. Simplified further to C2 squared, will be 2 into 1 minus n into P2 over P1, n minus 1 over n minus 1. And of course, the velocity at plane 2 will therefore be C2 will be equal to 2 into 1 minus n into P2, P1, n minus 1 over n minus 1, and we'll take the square root of that because we had C2 squared, so C2 square root of that. Now, we know that when we drew that graph for the duct, flow in the duct, showing the pressure, remember, we have P2, P1 equal to 0. Remember, we have A1, then we have V1, we have C1, we have C2, V2, A2. Remember that? And we know that, for example, in the nozzle, the pressure is decreasing. So the final pressure, P2, is 0. And that's where we have the maximum velocity. In the nozzle, for example, C2 max, let's call it max, let's put a subscript there, is when final pressure P2 is equals to 0 in the nozzle. So if we substitute that in that expression there, if we substitute that in the expression for C2, substitute that in the expression for C2, then we see that C2 maximum velocity will be when P2 is 0. So this quantity here will vanish, will be 0. So that will be minus 1. So what are we going to have? We are going to have minus 2 over 1 minus n, because what do we have here? This is now 0 at that particular point. And of course, this is, we have the square root, since P2 over P1 is equals to 0. So we'll have that expression for C2 max, that's the maximum pressure, will be given by C2. Therefore, C2 maximum, that's the maximum velocity, is equal to 2 over n minus 1 square root. That is the maximum velocity. The flow in the duct will be 2 over n minus 1. Remember, that's the asymptotic index of expansion, expansion index, and we have square root of that. And I've told you that, for example, when you're talking of steam, the wet vapor, that n will have a value of about 1.135, and in the superheat region, it will be about 1.3. So let's stop at this particular point. We are continuing with our lectures on the steady flows and jet propulsion, and we'll pick up from there next time.